Okay. So, hello from my side. My name is Luca Bertoncel. I'm responsible for R&D at the company Iskra SD. And today I will be presenting you a topic which is not directly related to casting itself, but it's a, I would say, combination of casting and plastic injection molding and joining. So, first of all, just a few brief slides about the company. I won't be too boring with this. So in general, we're focused on automotive and commercial vehicles. This is our main focus, but as well, we're present in medicine, electronics, and other relevant industries. And we work together with the usual suspects from the automotive, so mainly Tier 1 suppliers. Our focus was originally in high-precision single material components, such as plastic parts from technical polymers, aluminium pressure aluminium casting, turning, machining, and electroplating. But in the last 5 years, we are really focused in multi-material hybrid solutions, meaning that you join metals and polymers, because in some cases you need mechanical strength from metals, but then you need some other properties from polymers, which cannot be substituted with other metals. So it means we always try to combine these different manufacturing technologies, such as plastic injection molding, casting, machining, turning, to then develop and produce unique hybrid solutions. So we have two proprietary technologies that we see as definitely a benefit for the challenges in the upcoming future. The first one being is laser fusion, and the second one, which I'll be presenting today, is SonoFusion. So just in short, laser fusion is basically surface modification of metal surfaces for consequent injection over molding or on molding of polymers. So basically you avoid using glues or plasma treatment or any other surface activation methods to join polymers and metals together. And SonoFusion, the difference is that you prefabricate the polymer and metal part, and then you consequently join them together. So today I will be presenting the following technology. But perhaps in short, we should just have a look why would such a solution make sense for the upcoming challenges. So we know that especially in automotive, but also other industry, size matters. And I would say that there are two major trends that we see right now. So on one side, you have larger and larger structural components, gigacastings, which Tesla has started. Now also Volkswagen presented their own first gigacasting or megacasting, as they're calling it. So we see that the structural parts are increasing in size because cars are a commoditized product now. It means everyone tries to manufacture a car with the least amount of components necessary to have the desired function. On the other side, we have propulsion units, which we see are shrinking in size, meaning because of higher efficiencies of electric motors, of powertrain units, the powertrain units itself are reducing in size and the power density is increasing. So our company is especially focused on the right side. Also, the trends of the e-mobility itself, we see that in the last 2 or 3 years there was a very harsh market push for electric vehicles. Now we see that we have a record number of new electric vehicles being registered, and obviously in the upcoming years we see that this trend will most likely keep on going. But every single electric car is facing the same problem, so thermal management. How to regulate temperature, how to remove the heat from the areas where it's not necessary or not needed, and take the heat to the locations where it is needed. And we can see from one of the presentations of Canon, everything evolves around thermal management. The same philosophy also applies for AI computing. So last year we visited in Hamburg the AI computing fair, where also AMD, NVIDIA, and other OEMs in the computer industry are showcasing their thermal management solutions. And you can see that the same philosophy, how to remove heat from areas where heat is not wanted, how they're solving it. So we see that the same challenges arise in both industries. And if you also check the development goals of ZF, so a German Tier 1 supplier, you can see that for their electric motor design, cooling is in the center. It means everything involves cooling, which means that in e-mobility, to increase the efficiency, you need to have good or highly technically well-suited thermal management solutions. So what is active cooling, which I have been mentioning quite a bit? So if you ask any of the AI softwares or LLMs, you can see that it's basically active cooling in contrary to passive cooling. It means you need a pump or you need some kind of a system that pushes a fluid to remove the heat from unwanted areas. So if you first take a look at passive cooling, so if you have a heat source, it can be a chip, it can be an electric motor, you basically just position on top material with high heat conductivity with some specific design features to increase the surface area. And basically you're limited more or less with the convection and radiation that is limited to the material characteristics and the design itself. So you're very limited how much heat you can take out. And we see this solution quite commonly in industrial electric motors, where you see all these fins to remove out the heat, or even in electrical applications where you have these heat sinks with different ribs, again, to improve the heat removal. But the main problem comes when we're speaking about powertrain units. So, for example, this is a graph, again, from ZF that shows how much of a difference an electric motor makes if it's actively cooled in contrary to passive cooling. It means you can have almost twice as higher continuous output power. So it means that it definitely makes sense to work on different kind of concepts and ways to actively cool either, let's say, the stator package, the rotor itself, or any powertrain or electrical components where you have high currents. High currents mean high heat losses. So active cooling itself is obviously not the cheapest solution because, again, you need a pump, you have leakage tightness challenges and so on, but the efficiency increase is so much higher that for high-end applications is definitely the future. So now if you take a very simple active cooling concept and again just upgrade our passive cooling from before, you basically just need some kind of a cooling channel that is integrated inside the heatsink, and then you need a pump that pushes the medium through. So in this case, it means you have forced conduction, which will remove most of the heat, or it will be the main mechanism to remove the excessive heat. So in practice, it means you have a heat source, then you put a heatsink, so a metal that has high heat conductivity. It can be a high-pressure die casting part, even though aluminium alloys for casting, due to high silicium, have much lower conductivity as, let's say, standard aluminium. And then you need a cover to cover everything up, and an inlet and outlet to push the medium through. And obviously, in the end, you need a pump that will push the glycol or whatever you might be using to remove the excessive heat. And the main question, obviously, is how to design or manufacture such an actively cooled subassembly or component that will work in different operating conditions and that will also be cost efficient. So right now, I would say that you have three main technologies on the market that are addressing this challenge. So obviously, you can have a standard assembly where you have a aluminum housing, you have a metal cover, you have machined inlets, outlets, you have a sealing in between, and then you have some screws to join everything together. So this is a very good solution if you have small quantities, meaning, let's say, a few hundred, a few thousand parts. As soon as you have a few 100,000 parts, it means you need to tighten a lot of screws, you need to have a lot of sealings. It's very challenging to have a good leakage tightness system. So a lot of different assembly steps are needed to manufacture such a subassembly. Now, the second one is friction stir welding, which I'm sure many of the companies today are also showcasing, and it's a great solution, especially, I would say, for larger components. But the main problem here, I would say, is that you first of all need quite complex and expensive clamping systems to hold the part together during the welding process. And you also have a friction stir welding tool that eventually wears out, it can break. So you need to monitor a lot of different parameters to really have a good solution. And normally you also need some additional machining to remove the burr. And the third solution, which I think is now substituting friction stir welding in many cases, is laser welding, which has been already presented in the last two Eurogoose fairs. A lot of suppliers are now focusing on this. I think it's definitely the way forward. But you're limited in terms of the material selection, and it's more or less just a direct substitute to friction stir welding. So the technology that I'm going to showcase briefly is the fourth solution that we're proposing. It's not a universal solution, but it's definitely a solution, I would say, for smaller actively cooled parts, meaning between up to 300 millimeters in size, where we basically remove the metal cover on top and we substitute it with a polymer cover. So again, it means the basic logic is you have an aluminium or any kind of metal heatsink, and then a polymer cover with integrated inlets and outlets on top. So I will showcase this technology on one of the current projects that we are working on together with our development partner and also Tier 1 supplier. It's for the application of a coolant heater. So basically the same logic, just to first show you a schematic to understand. You have a heat source or a heater which heats up the aluminum heatsink. Then the aluminum heatsink, which is hot due to the heater, basically heats up the glycol that flows through the channels. So a pump pushes cold glycol through the casting, and then hot glycol exits the part. This is the basic operation of this sub-assembly. So obviously there were some development steps so that we designed the right design of the fins. So our the partner made several iterations in terms to reach the best flow, the best heat removal from the aluminum to the medium. And we also did several simulations to really also make the part manufacturable, to have obviously all these low porosities, low gas porosities, so all the usual suspects from casting. And on the other side, also a lot of effort was put on the design of the polymer part, because it needs to be flat, and also on the polymer selection itself, because even though many of the casters are not so well informed about polymers, polymers in many cases, even mechanically, are better or can be better than cast materials. And that's why we also proceeded towards this direction of substituting metal covers with polymer covers. So how does it work? Or just in short, I would say a simplified manner. So we have a metal part which we laser treat. So we develop a specific design of the surface structure which acts as small mechanical lock. And then we have a prefabricated polymer cover. We preheat the welding area, and then we join everything together. So this is a very, very simplified concept just for you to understand the basic logic. Also to show you the process flow, it's a very short one. So here we have the part. So we do first the structuring process. Then in the next stage, we preheat the welding area. And then after the preheating the heating head is removed, the parts are permanently joined together. So as you can see, it's a very short, simple process that removes several additional steps that you would normally find either with friction stir welding or perhaps laser welding or standard assembly process. So this is one of the first prototypes that we produced. You can also check it out at our booth. We're right now also doing burst pressure tests, fatigue tests. As you can see, we've been right now able to reach up to 7 bars of burst pressure. And I think the most important point here is that you can see that the welded area, or the area that is structured, was stronger from the polymer itself, because you can see that the polymer cover at burst test broke around the welding area. So the weld itself withstood the required pressures. So 7 bars, I think, is more than enough, because the majority of applications in this active thermal management will be around 2 to 3 bars, somewhere in this range, depending on the use case of the customer. So we have also a transparent part. This is polycarbonate for you just to see through, to understand a bit better. So you can also check this part at our booth, just to get a bit more fun experience how this design works. So I think if you now compare again in the table together with standard assembly, friction stir welding, laser welding, our solution, I would say that the main benefit that we see is definitely, first of all, the simplicity. Because I'm sure that many of you who are not from the plastic injection molding are not familiar how much of design freedom injection molding really offers you. So it means with injection molding we can simply integrate the inlet and outlet connectors without some additional inserts. So because the tool complexity can be much higher, the design complexity can be much higher, and you have much more design freedom. Also, if you, for example, would want to have some metal inserts to be also in-molded in the cover itself, that is also possible. So you can add a lot of additional features, a lot of additional functionalities in the cover itself, which would normally not be possible with, let's say, casting or with stamped covers. Also, in terms of the investments or just the process flow, you can see that in this case you need just a plastic injection molding tool. You need a casting tool if this component is cast. This component could also be, let's say, stamped, deep drawn. It doesn't need to be cast. So just in terms of capex, you can be more cost efficient and also more energy efficient, which I think nowadays, if you like it or not, is one of the very important metrics to follow. So I would say the main benefits of this technology in comparison with others, first of all, if you just compare with standard assembly, you saw that you get rid of a lot of additional components, screws, sealings, and so on. Also, the process itself, the assembly process flow is much, much shorter. So also reduction of CO2 footprint because, for example, what also many, I would say, people from casting are not familiar with, polymers itself, especially technical polymers, are much, much more expensive per kilogram as aluminum alloys. So let's say if a 226 aluminum alloy costs around 2 euros, a technical polymer may cost around 4 to 5, even 6 euros per kilogram. But the part cost of the polymer cover in the end will be 50% or even higher, cheaper from the casting. Why? Because you only need an injection molding tool, which is 10 times the lifetime of a casting tool. You don't need any additional trimming tools or any additional machining. And also the energy consumption of injection molding is much, much lower because you normally injection mold polymers at around 280 or 300 degrees Celsius, while you cast at 600, 650 or whatever degrees. So the energy consumption is much lower, and obviously also the process flow is lower, which eventually results in much lower cost of the part itself. Obviously, you can reach much, much higher design flexibility. More complex parts can be injection molded than they can be cast. And also, as already presented and mentioned, the overall process flow is also much shorter. It also allows you a very high automation level because, as you saw, you basically just need a press, a preheating unit, and a press to join the parts together. No really complex solutions to get the parts together. And another benefit for sure is also the design and material selection versatility, because you don't really need a high technical polymer if your application, let's say, only needs up to 50, 60, 70, or 80 degrees Celsius. You can take a very cheap technical polymer, or if you have temperatures up to 140, 150 degrees Celsius, you can use a PPS, which is a very high technical polymer with high operating temperatures. So you're very versatile in terms of what you want to achieve. We can then adjust the material selection and obviously also adjust the design itself to meet your requirements. And as mentioned already a few times, I think cost is probably the main word in automotive. Even if you work long enough in automotive, you wake up with cost every day. So everyone just speaks about cost. I guess if you have a good technology and if it's not cost beneficial in comparison with other solutions, no one really cares. So this is definitely also one of the important points to highlight. So this was in short. If you have any questions, let me know. You can also send me an email, call me, and I'm sure we can have a talk and see if our technology can suit your requirements and demands.